Sujata ma'am?
Yes, sir. Yes, sir. I joined, sir. Ma'am will join within 2 minutes, sir. Good afternoon, sir.
Okay. Good afternoon, ma'am. Okay.
Good afternoon.
Once ma'am will join, we'll start the session.
Yes, sir. Yes, sir.
Okay. Okay.
Good afternoon, ma'am. Welcome, ma'am.
Good afternoon, ma'am.
Good afternoon.
Welcome, ma'am.
Yeah, good afternoon. You can hear me?
Yes, ma'am. We can hear you.
Yeah. So,
Sir, shall we
Yeah,
start?
yes, ma'am. We'll start.
yes,
We'll
yes,
start.
yes.
Okay. Good afternoon. On behalf of the Department of Mathematics, Little Flower Degree College, Uppal, Telangana, and PG and Research Department of Mathematics, Auxilium College, Vellur, Tamil Nadu, it's my pleasure to welcome you all for the third day session of a 5-day national level online PDP on writing research articles in mathematics and statistics. A day without prayer is a day without blessings, and a life without prayer is a life without power. To start with, let us invoke God's blessings through the prayer song followed by the prayer service. Over to the students.
Let there be love shared among us. Let there be love in our eyes. May now your love sweep this nation. Cause us, so Lord, to arise. Give us a fresh understanding of sisterly love that is real. Let there be love shared among us. Let there be love. Let there be peace shared among us. Let there be peace in our eyes. May now your peace sweep this nation. Cause us, O Lord, to arise. Give us a fresh understanding of sisterly peace that is real. Let there be peace shared among us. Let there be peace.
Give us today, O God, the mind which can really learn. Give us the attentive mind that we may concentrate all the time on what we are learning and doing. The retentive mind that we may not hear and forget, but that we may grasp a thing and remember it. The open mind that no prejudice may blind us to truth. We do not wish to see. The eager mind that we may not be content to remain as we are, but that every day we may try to add something new to our store of knowledge and of skill, and of something finer to has store of goodness. Amen.
Thank you, girls. Now, Ms. Priya, Assistant Professor, PG and Research Department of Mathematics, Auxilium College, will welcome and introduce our resource person of the day, Dr. Indrani Pramod Kelkar. Over to Ms. Priya.
Good afternoon to one. Good afternoon to all. I am privileged to introduce our resource person of the day, Dr. Indrani Pramod Kelkar. She completed her BSc in Mathematics at Pune University and MSc in IIT Bombay. She started her career as a teacher at SNDT Polytechnic, Mumbai. Dr. Indrani Pramod Kelkar worked as a professor in mathematics in Vignes Institute of Information Technology, Visakhapatnam. There, she headed the Department of Training and Placement. Her profession continued in DGM Academics Gate, Hyderabad. Ma'am entertained as a professor in mathematics, chief mentor, and associate R&D in Acharya Institute, Bangalore. She also worked as the assistant vice president of academics, Think Cell Learning Solution, Hyderabad. At present, Dr. Indrani Pramod Kelkar works as a subject admin, engineering, and basic science at TCS ION, Hyderabad. Dr. Indrani Pramod Kelkar has presented more than 20 papers in the national and the international conference and published more than 30 research papers in national and international journals. She has written 4 books to benefit engineering students. She was a trainer for National Olympiad at IIC Bangalore, also a trainer of Vedic mathematics, soft skills, and life skills. She received Master Trainer certification by Vibro Mission 10X. Dr. Indrani Pramod Kelkar coordinated many seminars and FDPs. Once again, I welcome one and all. Thank you.
Thank you, Ms. Priya. I now invite our resource person to take over the session. Participants, you can post your questions in the chat box, which will be clarified during the question session. Ma'am, you can take over the session, ma'am.
Thank you, madam. And thank you for the wonderful starting of the session. I will share my screen so that I can present the presentation on mathematical modeling. Once it is visible, please let me know.
Yes, ma'am. It is visible. Yes, ma'am.
Yeah. So thank you so much. And I'll not be able to see the chat because the screen shows only the presentation. So if there are any questions, madam, you please let me know. I'll answer them on.
Yes, ma'am, surely.
Yeah, thank you. So this is something about mathematical modeling. I, being with industry as well as institutes, have understood that modeling is a very important aspect of the engineering industry. As well, today, every publication in engineering or in science, if it contains a mathematical model, has a well-received understanding from the publishers as well as the researchers. So this is a very important topic, and at the outset, I want to thank Madam and the Auxilium College, where I have visited once in 2019 and have a very good rapport with them. So it was a very great opportunity for me to meet all of you virtually post this pandemic session, and hope sometime we can meet again in the physical form. Thank you so much for this opportunity, madam, and I shall now introduce what is mathematical modeling process. So a mathematical model is a mathematical relation that describes some real life situation. So we have around us any real life situation. It is almost possible for 99% of the things to describe it mathematically. But we have to understand the real world. People who are looking at solving problems may not understand the language of mathematics. So what is essential is there will be a problem in real world. It may be sometimes very vague, not very clearly specified like mathematical problem. So we have to make it into well-defined problem. Look for the mathematics possibility inside. Make some starting assumptions. Assumptions are a very important part while making a mathematical model, because for complete solution at a time, we may not be able to make a mathematical process. For some part of it, we begin with, and then we extend it to give the complete solution. So once we have set the assumptions, it will tell us what kind of mathematics is possible to apply. So the governing equations will be decided by the mathematician who understands what type of problem it is mathematically, whether it's analytical, whether it's stochastic or probabilistic, or it is a very simple numerical problem like what we have been solving in school called as word problems. So they can be converted. A word problem is a real life problem, can be converted by substituting an appropriate formula, solve it, and then interpret it. So a simple example of a mathematical model is what we have studied in school. Like if 1 dozen banana cost 20 rupees, what would be the cost of 1 banana? Now, this is a real life problem. We have to write it in appropriate form. get the governing equation, whether it's linear, non-linear. A mathematics person should understand it, get to the solution, and then validate it with different data. Now, when the problem is not as simple as the 1 dozen banana to 1 banana, we need to know different data points. So important part as far as the real world problems are concerned is not only making the mathematical part of it, but finding out that data for which all kinds of possible data values for which the solution is satisfying, or we have to specify where it is not specified. Then after that validation, we should go to find out the implication, or in other words, articulation in terms of a problem which is understood by the real world situation. That is, it could be a biologist, it could be a physicist, it could be an accountant, it could be a computer scientist who has given us that real world problem. From the mathematical part, it must be interpreted into a language which that layman of mathematics can understand. So this is a mathematical modeling process in general. If we look at what are the different types of mathematical models, basically there are two major types called empirical or theoretical. Empirical has another two observations or experiments. Observations could be simply like data collection or looking at particular situation and noting down the observations about it, like temperature, pressure, and then going with it, or processing an experiment, collecting the data. So empirical model will definitely need some kind of data processed through experiment or observation. Theoretical models will not have necessarily the data, but it will be majorly talking about something which is extrapolating that data. Not necessary to have too much of data, but little observation, how we can extrapolate it either statistically, which we call probabilistic model, or mathematical, which gives you like differential equation or linear equation or matrices, and then computational, where actually an algorithm can be written and the solution can be found. Different types of models can be developed depending on what kind of problem is there. So major types are 6: static or dynamic, discrete or continuous, deterministic or probabilistic, linear or nonlinear, explicit or implicit, qualitative or quantitative. Now, the approach is dependent on what is the kind of output expected, what kind of data is available, and what is that mathematical process we need to adopt. Depending on that, this type will get set to the model. It is not that we wish to make it static or we wish to make it dynamic. It depends on what kind of a physical phenomena is happening. To that, what is possible, because we may not be solving the complete solution, as I said before also. We may give a mathematical model for a particular part of it, then it is possible that some part of it is static, but in totality it is dynamic. Or some part of it behaves linear, but in totality it may behave non-linear. So we cannot say it completely very well. Distinguishing characteristic can be found for a complete mathematical model, but part of it can always be specified by understanding the data, the input which we get, the method which we need to adopt so that the data satisfies the expected output. Now, when it's static or dynamic model, a static model, or we call it as a steady state model, basically calculates the equilibrium. And what does that mean is it does not change with respect to time. So it's time invariant. So even if there is change in time, there won't be any change in the state of equilibrium. Such a model is called static. Static does not mean nothing moves in that case, but it means that there is no parameter called time required, which is understood as a variable. In dynamic model, time will definitely be a part of kind of a parameter on which the whole system will depend. So static and dynamic basically differentiates between it varies with time or it does not vary with time. So another important thing is dynamic model will come like a differential equation. For example, you can take a simple thing from a stationary vehicle which starts moving and they say rate of change of its velocity. So it is like the displacement divided by the time, and you call it velocity or acceleration, where you get rate of change with respect to time. So that would be a dynamic model. More the number of changes happen, there will be, instead of simple derivative, there will be a differential equation which will come. Discrete or continuous model, what it means is a discrete model treats objects as independent or discrete or not having a previous state to next state relationship. So it's something like molecular model. Continuous is a process in which the objects move depending on its previous state to next state. There is a connection. So like a flow of blood in our body, or flow of water into a pipe, or change of temperature when water is put for boiling, or the travel of electricity and the magnetic field getting generated. These will be continuous models, but discrete models are the ones where you have, say, a digital timer. You put that at tick, 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 it's going. So every tick is discrete. Then that kind of a model is called discrete. I feel that you should understand these all types well before you start the mathematical modeling process, because once you know the variety of types, you will be able to decide, when you look at the problem, which kind of model will suit to given problem. And that's why it's essential to understand the differentiation between these types. Deterministic or non-deterministic, as it is called in computer science, or we call it mathematically probabilistic or stochastic model. So deterministic model means if we know given set of sets or the states of a particular situation, given those initial states, we can definitely determine the behavior, what would be the next state after particular process or after particular operation. Like if we boil water, we definitely know it will convert into a vapor. Not that we don't know what happens the next state. So next state is not unknown, but it is a known state. Such a thing is called a deterministic model. Probabilistic model is where exact prediction of next state may not come, or a unique value of next state may not come. There could be 2 or 3 different possibilities, and any one of them could be a possible answer. In such case, it is called probabilistic model, and for each of those possible states, what would be its probability of getting? Like if you toss a coin, whether it's head or tail, one can never say it should be head or tail. We'll say that 50% chance that it could be head, 50% chance that it would be tail. So if we take the activity as tossing a coin, what is the next state? That is, after tossing the coin, what is the state the coin goes into is a probabilistic model, not deterministic model. But if that coin is tampered, that we have put some weight on one side, then that activity becomes a deterministic model. So sometimes we need to do some cleanup to make the real understanding of the next state being deterministic or probabilistic. Linear and non-linear. This would be very easy as mathematics people to understand, because we know linear equations and non-linear equations. We know linear means degree 1. Now, whether it is at linear equation in one variable, two variable, and simple variable equations or differential equations, we will have the linearness in it. That is, there is a direct relationship between two variables. That is, if y is a dependent variable on x, y varies linearly with respect to x, then the model between x and y will follow a linear model type. Non-linear model is the relation between the parameters or the variables is not linear. It could be quadratic, it could be cubic, it could be higher degree. Like throwing a ball on to a cricket ball. You have seen the commentary, and then after a ball is thrown by a bowler, lot of graphics and lot of analysis will be done to the ball, and that trajectory of that ball before it is put and after it is put, there will be a matching done. That is something like a non-linear model or a parabolic model, the degree 2 or degree 3 model required. So linear is where the relationship between the variable dependent and independent is straight. It doesn't need any powers or reciprocals or roots. But non-linear is the relation between the dependent and independent variable cannot be written with degree 1, but it needs either powers, reciprocal, or in roots. Explicit and implicit model. Explicit model is the state of a system where you can say that what was before and what's going to be now and what's going to be later can be explicitly stated in terms of what was the previous state to next state. But implicit model is we may have to write it in terms of an equation or in terms of a state where some more calculation would be required to know exact value. Like for example, you write simple equation is y equal to x square. Now we know it is non-linear, but it is still explicit. But we write x square plus y square equal to some kind of a variable square, not necessarily a constant square. Then what happens is we'll have to write y in terms of x, though we know y is independent, y is dependent and x is independent, but the relation between them is obtained in such a way that we cannot write y as a function of x. That's what you call explicit function and implicit function. A similar understanding extended is explicit model and implicit model. Qualitative and quantitative model. These two are very, 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 very important as far as real life problems are to be put mathematically. Because quantitative model needs to give some kind of numerical answers or values at the end. But qualitative model is not necessarily looking at data. It's not necessarily looking at numerical data or quantified data. It's talking about, like, suppose in pandemic last 2 years, a qualitative mathematical model was what was the mental state of students who could not go to college or school to study. Now that need not be a quantitative model, but it can be a qualitative model stating that these were the different experiences of people which are represented by different mental states and what was majority of the state experience. And then we talk about the quantitative model exactly for pandemic was what is the number of people who got impacted or who got affected by corona, how many people took the vaccine, of the people who took vaccine, how many were saved, how many even after taking vaccine got impacted. That would be a quantitative model where we talk about number of people, number of things, number of situations. But in a qualitative model, we will not be talking about number of, but we would be talking about kind of an ecosystem between the observation done between people. It could be about animals, it could be about plants, and we just talk about a quality of the reasoning, not about the quantity of the number of would not be necessary. And many a times it is not necessary to have a quantitative model because we just want to know whether administration of a particular process in an industry will help the people operating that in a better way or not. Now we just want to know what would be the impact, because we definitely know number of people who will get impacted, but whether the impact will be a better impact or a bad impact, that would be a qualitative model. Now, we have seen all these types of models, but major two things which come into real life problem, which we want to convert into a mathematical model, is a black box model or a white box model. Black box model is we have no prior information and we are looking into dark, finding out solution. For example, if you would think 20 years back that there could be a cell phone which can start your AC at home when you are sitting in the car, it would not be anybody's thought process 20 or 30 years before. But today it has become possible. So there was no data available, nobody thought about it, nothing was done, but still it is possible to think out of the box and get to solution. Or another example of a black box model I can tell you is that ATM machine which is put into every street today, possibly around 10-15 years before, when we used to go to a bank to withdraw money and we used to wait for bank holiday, bank timings, after 2 o'clock you cannot draw money, a lot of restrictions were there. There was no data available. Nobody would think that any time money could be possible for us to draw because it's my money into my account. How can somebody, because they close the bank, they will not give me my money when I need it? So that was a black box model which somebody thought about and made into a possibility. Today, we have a lot of new models which came out, because in the beginning, we had that if you have an account with State Bank of India, you have to go to State Bank of India ATM only, and then you can draw the money. That became a restriction because of the model that time which was operating. Later, somebody thought, if State Bank ATM is very far where I stay, why can't I take out the money from some other bank? And that became a possibility. So black box model is something where no prior information or no previous data is available, and still there will not be any physical structure which will be made, but a mathematical thought process will be developed. Look for its possibility, look for its issues, what could come up. Are there any problems in handling it? Will be thought, understood mathematically, and then a physical structure will be made into. White box model is we have all the necessary data. It's like we are doing a survey or we are doing experiment and getting the results. We are noting down like temperature or pressure or the reaction between the gases or the flow of water from one place to another. We want to put a pipeline from one place to another. What is the contour? All data is available. Now to fit that data, we create a model is called a white box model. So black box model was not a concept for say 30-50 years before. Nobody would think about black box model because most of the time we looked at deterministic or something which takes known information converting into a different form, that only was called as mathematics or modeling process. But black box model has come in with the invent of computer, with the invent of new technology, and with the invent of man wanting to make things more and more comfortable for himself and herself. It became necessity for people to discover things which are beyond imagination of some people. And then this became two different important types. So we should know whether whenever in industry we look for making a mathematical model, the first question will be asked is it black box or white box? Means, do I have to extrapolate what is not there, or I can interpolate from the data which is available and reach to a suitable solution. So what is a linear model? It looks very comfortable for you, like y equal to x kind of a graph, or it could be any y equal to mx plus c kind of a graph. And what happens is there is direct relationship between the variables, and you will know you will fit like your least square method or different regression line process, or you can do the best fit to the data and look for. So all these models which I'm showing you examples are formed by using the line of best fit process or the regression, linear regression process. So if the data best fit comes out to be linear, then we say it's a linear model. But the best fit is, for some part it is linear, but not all through. And this is a major mistake which happens many a times. If we look at data between, like if you look at the data which is right above the red line up, the red line which you see at the bottom, and beside that, if you go right, it will almost look like a straight line. But before that, it behaves differently. So it's like exponentially. In the beginning, it is slow and then increases very fast. But later, it looks like almost straight line. So it depends on what kind of data you have got. So if your data is not appropriate, then validation to the model which you fit will not be appropriate. So natural situations like you have seen the growth model or the decay model, the population model, these are all exponential models. Quadratic model, it is naturally the sinusoidal kind of process, or part of the sinusoidal where there is a wave or there is a projectile, like I said, throwing of a ball or throwing of a, or the travel of an aeroplane or travel of a rocket. These are all kind of quadratic or projectile models. Then trigonometric model, they are more, I mean, quadratic, they may look in some part, but the wave kind of processing, then it could be a combination of sine and cos together. And we call trigonometric models also as circular or cyclic models, because to define that, you will not be able to do it with 2 parameters. You need the 4 parameters, that is the longitudinal traversal, what is the vertical up and down traversal, and what's the distance between. That is the waveform needs its wavelength, its amplitude, all that should be specified. So it can't be done with 2 parameters, which would be with quadratic model. But this kind of sinusoidal model, as also it is called, or circular functions as it is called, it will need more parameters. Then you have to be very careful that if there are independent variables are many, and then there is one variable which depends on many of them. Like for example, if we are looking at growth of an individual, previously it was always looked at, it is sufficient to know whether what age, what should be your height and weight. Now today it is specified that it is not necessary that the table which the doctors used to have before should satisfy exactly just age to the height and weight relationship. Sex matters, whether gender matters, whether it's a boy or girl. It also matters which tropic of the world we come from, whether we come from West, East, or African, or which tropic we come from, because there the data differs. Also the food habits, also the lifestyle, all these have now parameters which are come into. So we cannot say if we took few parameters and make a model, it may not fit every possible data. And other different models which are available is cubic, which is generally not what comes in, and unless you are looking for something which is 3-dimensional. But reciprocal is a very important model where things go in inverse proportion. So exactly what was the increasing or the exponential model, its opposite could sometimes follow the reciprocal model. Then logarithmic model and the logistic model. Logistic is a model where there are 2 asymptotes, that is 2 are the 2 times 2 horizontal lines will define the way the wave moves. So it has its own maximum and minimum will be available. Then that's the logistic model. Now all these I showed you because when you get the data, you must do the first simplest thing mathematically. What we do is find the best fit using the linear regression process. Look how the data looks to behave. If that, and this can be done using computer today, you don't have to do it by actually fitting equation with, because in your mathematics schools or colleges, you study data which is maximum 10-15 items, but 10-15 data points will never tell you what the general behavior is. We should have thousands or lakhs of data. Now, if that size of data, if we are using, we have to take the help of computer or computational process, and then we get the actual real fit to the data. Then we decide what kind of a model it looks. Then we look for its equations. So now, if we have to do mathematical modeling, to be classifying, we saw different types. We saw black box, white box. We saw it's the best fit will tell us what kind of an equation we should look for, whether we should look for a linear, quadratic, logarithmic, exponential, what kind of mathematical equation would fit. Now, to decide that, what are those parameters we should look for is the complexity of the object of study. So if the object of study is, for example, the COVID impact in India. Now, the complexity is so high because the age groups matter, the comorbidity patients behave differently, younger generation behave differently, people with vaccination behave differently, people without vaccination behave differently, people who traveled behave differently, people who were at home behave differently. So complexity is definitely to be understood before we take a decision of which model or which mathematical process we have to put. Next is the operators. What are the parameters we are going to look for? So anytime when we want to get a mathematical model, we should not think about complete problem. That is what I said in the beginning also. We should go on looking at different types, different like shorter problem, smaller problem, and then go on expanding it. Then what are the parameters? You model the operators first, then model the parameters, and then what is the goal? What is that we want to prove? What is that we want to see? If that is known, because that should be decided pre-hand before we set the mathematical model. Otherwise, the inference will not be appropriate. We may change that goal by the observation of the model, but we should have some goal set, and then we do, like probabilistically, you do the testing of hypothesis. So when you use the testing of hypothesis process, you have to set the null hypothesis and the alternate hypothesis. So exactly same thing. What is the goal modeling is, you set the null hypothesis, you set the alternate hypothesis, and now fit your probabilistic model there to check which of the hypotheses can be accepted and which can be rejected. And then actually which implementation method we can adopt, that also depends on the size of data. Whether we want to do computational method, we want to use algorithmic, or we just want to do statistical, where we want only probability function is defined and we say that that's sufficient. We don't want to actually get every value at every x, we don't want the value of y, but we want it at some points. Then we can decide the method by which we want to do the final implementation. So basically, if you decide what is the object of study, then you have simple models where the object of study are very, very simple parameters. But if there are objects with system is like there are like you have already set processes, like industry is mechanical industry or electrical car to be possibly coming on the road or not, then it's a system, because there is already some mechanical process available. You want to interpret into that something else. So you have to not go by simple model, but go by object system model. Then structural object system and simulation. Simulation, I can give you a simple example. Today, if you want to learn driving, car driving, when you go to the driving school or you go to the Maruti or any kind of a vendor, whether it's he is telling you that we sell you car, but before that we'll give you that kind of a experience of simulation. You would observe that they would make that simulation so fantastic that you feel as if you are into the car. So what simulation is, the virtual reality, as if you are driving, you will feel, but you would be stationary, you would be inside the very enclosed, nice place where you are safe, no possibility of accident, no possibility of somebody else coming on the road in front of you. But still, the environment will be made virtually such that you can simulate the experience of. So simulation becomes very important when we want to go with a model which can have some endangering situations, like a flight pilot would get into simulation, or car driving could get into simulation, or a computer program which goes on for large data on health model, it goes into simulation. So simple models are the ones which we do generally at research, but simulation models are which we come into real life. Then model based on model operator, you can decide what's linear, non-linear, algorithmic, simple or complex, depending on the best data fit what we have processed. Next is, what is a non-linear model? I already told you it will have a non-linear, generally differential equation in large case. Linear model will have linear differential equation and superposition can be applied, whereas in non-linear, their superposition rule cannot be applied. Distributed models where you will have, now I'm coming to where which kind of mathematics will be applied in. So you have either differential equation where you have linear or non-linear, and there is single parameter processing. But if you have distributed parameters or more parameters on which the total thing depends, like time and place is what on which the whole system or the physical process depends, then you cannot do a one variable model, but you will need a distributed model, or we call it as a partial differential in terms of mathematics, because it needs two variables, though there is a differential, though there is rate of change, but the dependency is on both time and location or place. Next is lumped models. Lumped models are the ones where the parameters are concentrated at single point. So they are not distributed, they are not two different things, and they are not looking different, or their physical appearance is not different, but they are at one place. Such a model will need ordinary differential equation, because we will call all the parameters representing one single parameter and make it into ordinary differential equation with single variable processing. So time varying models where you will get not one differential equation, but you will get sometimes system of differential equations, and the right hand side will be a time varying coefficient. You will not get a constant or a function of n, but you will get a time varying coefficients in the differential equation and the right hand side also. So this becomes more complicated, more difficult for you. And continuous models are where you simply get a differential equation if it is single variable, x depending on time or x depending on temperature. It's called continuous model. And discrete model is you will not be able to write it as a continuous function, but you will write it as a function of different states. So you will get a difference equation, not differential equation. So you have studied difference equations. So this will be a discrete model will be represented. So please understand, depending on the type of model, it automatically tells you what kind of a mathematical formulation is required. So depending on the way the parameters behave with each other, it tells a mathematics person that what kind of mathematics, whether partial or whether ordinary differential or whether system of equations or whether it is difference equation, it will all depend on what is the parameter behavior. Next is mathematical model, why it should be put in and what does it do to us? What are the advantages? So it allows better understanding how the system works even without operating the system actually. So without even constructing the whole process, you are doing only thinking. And mathematics is something very beautiful that you can create in your mind before it gets created into the world. And that's what the engineers say, that science actually tells you how the nature behaves. Engineers create what humans can handle, but mathematicians connect the science and engineering by doing the work of that imagination or formulation into an abstract world. And that is why many people are scared of mathematics, because of its abstractness. But that abstractness converted into a appropriate model allows us to give an understanding, that is interpretation of your xyz gives an understanding whether the system works or it should not work. Then second is, it gives you a possible output, a possible response to possible input. So if this is the input, what should be the output? So in computer processing, we call it as a testing of the program. So we feed some data and check whether all these things work okay or not. And if they work okay, then only the program will be given to general public to use, stating that now any data you give, I have tested for all possible inputs, the output is the expected output as the program is supposed to give. Next is allows the user to understand the limitation or the boundaries within which the process has to be put, or conditions that this should not be done. Like if you know you have a washing machine at home, and if today you have a fuzzy washing machine, if you have bought it recently in last 5-6 years, if you have purchased a new washing machine, if it is an automatic washing machine, then it is called fuzzy washing machine, in the sense that you put the clothes in the washing machine. You must have seen the washing machine does some kind of whirling, chuck, chuck, chuck sound will come. That will tell how much is the weight of clothes which you have put in. Now the fuzzy washing machine will decide, it is mathematically programmed to find out for this weight, how much should be the water, how much should be the soap, how much should be the spinning required, how much time is required to complete the whole process. And now we say that the washing machine has become intelligent. But to make that washing machine intelligent was not something which was constructed washing machine or designed a washing machine. It was mathematically using the fuzzy logic. It was first decided mathematically, putting the parameters. What is the weight is the main important parameter, deciding the other parameters. So the extreme conditions, like the washing machine will tell you if its capacity is 10 kg and you put 13 or 15 kg of it, first whirling itself, it will stop and give you a red color E on the pin board on top of the machine, saying there is some error. If that means that the error will indicate there will be different types of errors. So what it does is, you have crossed the limit of the weight which the machine cannot handle. So instead of disturbing the machine, the extreme condition will be checked before the machine enters into that. And the maximum limit of weight, maximum limit, suppose the water is not entering the pipe is choked and water is not coming. Sometimes what happens in the old machines, the machine will get heated up and the machine backside, the whole process will burn out. But today the machines are so intelligent that if there is no water, inlet pipe is stuck, it will show you an error on the pin board, and then you know that there is some problem and the machine actually will not function. It is good that it saves your machine from. So this kind of a processing was all processed mathematically first, put the parameters of a washing process, then done the design. Then we got into a mode of from semi-automatic machine to automatic machine, and automatic machine to fuzzy machines. And today the machines are so intelligent that it will decide. You also know there is fuzzy air condition available today. If you purchase the new AC with the latest the best possible, the top end model, if you buy, like in an office, we have 100 people sitting inside a room. There is an AC working. It knows how many people are there. It has a sensor to know how many people would be breathing in and how much should be the temperature to be kept and how much should be how many ACs should be switched on. But if after an hour, this, like how we are having a seminar now, once the seminar is over, people disperse. And now only 5 or 10 people in one corner are having some discussion. In olden days, somebody has to go and switch off all the fans, all the ACs. Today, the intelligence has come to the system that it will sense that in this corner, 5 people are sitting. then only that nearby fan and AC, whatever the intelligent process made to that machine, will be on, and rest will be switched off automatically. And this is all done first mathematically when a model is made, which understand what's the input, what are the different input to different output processes, and what are its boundary conditions, as we call it, on which conditions beyond it will not work. So that's the extreme working conditions. All will be tested mathematically, and then the model will be made into a closed loop design, or we call it as a final form. And then it is stated that a working machine will be made with the conditions of extreme conditions, that in extreme condition the actual system will not work. So that this mathematical model is telling the new machines to be more safe for the machine. Operator is given the intelligence that you choose the program and the machine will work to its best capacity. And this all became possible in real life today, which we see. I mean, any common house today has these kind of, if it is purchased recently, you will find it has the best possible system which saves your electricity, it saves your machine, it saves the soap, it saves your water. All that is possible only because of the mathematical model which was tested and then converted into an physical model. So now, if let's see how a specialized application is required. So we can do mathematical model for everything, but it's not necessary always to create a mathematical model for complete process. Like I told you, the washing machine example, we need not make a washing machine mathematical model. We have to make a washing machine model for the drum size, then the water inlet process. Each will be a different process made. So water process is one model, soap process is one model, the drill process is one model, and then the scrubbing process is one model, spinning is one model. But now, finally, what is most important is all the processes are connected to each other. So what we say is the ending points or the boundary points, the equations must be satisfied, because finally the equations which are made for different processes, different mathematical equations, but what should happen is they must satisfy each other so that the mathematical model finally satisfies everything. So model is made independently, but what is important is the boundary conditions or the overlapping conditions are tested so that it becomes a efficient model. Like for example, you want a car which can drive by itself, an unmanned car, or we have today unmanned metro rail running, that the project coming up in India, and it's already there in some other countries. Now if it has to work, it cannot be actually made and then tested on many cars and then have accidents and then finally lose a lot of property. Every accident will have a lot of loss. So that will not be done, but what will be done is how that computerized or electronic process is made to the engine so that the engine becomes more and more intelligent, or today we call it as machine learning processing. So a model based on the parameters will be having so many things. So don't think that we can just decide, but what all I told you till now is put into this one chart. Different types, different processes, and different ways the parameters can be put in. So if you understand this one, you have to follow any one of these, or for each independent one, one box of it will come in. But understanding all this before you start the mathematical model for whatever data you want to process on, it's very important. All the varieties you should know. And then the goal has to be very properly set in. We have either a goal of a descriptive type, that means we say that we want this value to happen. Then we call it as a descriptive goal, that exactly this should be done or this should be achieved. Optimization is where you want to maximize or minimize, like you have done the linear programming problems, something similar to that. So you want to make a machine or you want to make a mathematical model which is improving its performance than before. So we say it's optimization model. So we are not saying that it is the best, but we say that it's better than the previous one. And decisional model, it's something like where you say yes or no, true or false, or to do or not to do, that kind of. So it will, you put in the data and it tells whether this is a valid or invalid data. That's it. So these are three goals to be appropriately put, because if it's a descriptive model, you need equations which give you correct solutions. You cannot have no solution state or infinite solution state there. Optimization model should know that you have improved, so that inequality condition should be appropriately set there. And a decision model will be more of a logical type of thing where you have a true false kind of data or 0-1 logic to be added in. Then models based on implementation method. Majority times people in mathematics think it has to be analytical model. And an analytical model will either be algebraic model where you have equations. We don't mean algebra means only linear equations or matrices and things like that. But analytical model with algebraic approach is where you have equations, and approximation is where you do numerical methods. So algebraic or approximate. Approximate is basically all your Runge-Kutta method or Newton-Raphson method and all those. They don't give you exact value, but they give you an approximate value. So analytical was the approach for many, many years when there was not good invent of computer. But today, the implementation method could be algorithmic, where you have numeric or simulation. Numeric is feed the data to the computer and you get the output. For example, you are using some kind of a app on your phone and you are playing a game, and then you are having experience of simulation, like you are driving a car but you are racing a game, and it's a simulation experience. Though it's a game, it is a model which is algorithmic with simulation. But numeric will be where you actually feed the data values and you get an output, but the process on that numeric data is by a computer algorithm or computer program. So algebraic, approximate, and numeric, there is little differentiation here. Algebraic approximate, you have some kind of formula, you put the data into that formula and get it, so you have some definite thing. But in numeric, it has to go through a lot of processes to reach to real answer. And simulation, I have told you already, with car driving or simulation or anything which you don't want to actually make it happen before you want to test it, feel it. It's more about feeling the whole thing. That is a simulation model. So now I have told you a lot of things about what modeling requires, but what are actual steps involved in mathematical modeling? So in last 15-20 minutes, we'll understand what are the steps involved in. So first step is formulation of the mathematical statement. So state the question, what it means. So real life, somebody will tell you their problem in terms of, say for example, when I was in IIT doing my MSc Mathematics, we had a problem given by the government of Maharashtra to my professor in IIT, and they said that they put a pipeline from Kalyan to Pune, and the pipeline water is actually getting stagnated at one point. Now, they stated the problem in their language. It was more of a civil engineering problem, that we put the pipeline, we don't know whether the contour is okay or not. We don't know whether slopes are okay or not. We don't know whether the size of the pipe, the diameter, all that is okay or not. But there is an issue that at one point the water is not flowing ahead. Now, my teacher, he gave a blood flow modeling, like what you do fluid mechanics. So he converted the whole language of a civil engineer into a mathematics called fluid mechanics, then understood what are the parameters, what are the dimensions, converted into a complete fluid mechanics problem. That is like stating the question in mathematical way, identifying the relevant factor. So the real life person who is telling his issue or telling his problem will tell lot of things about, because he is actually in pain, he's suffering, he is not able to solve the problem. Not pain means physical pain or something, but he is in pain that he is not able to solve a particular real life problem. But when we convert it into mathematical form, it is essential that we find out what are the relevant factors out of all what he said to make it mathematically viable. So write that formulation in terms of the mathematical description with parameters, with the type like linear, nonlinear, discrete, continuous. All the previous half an hour, whatever I told you, will be required to be used while making the formulation. Once the formulation is done appropriately, then it's not very big deal as mathematics person, because then you have decided the set of equations, you have come to a point, now you have to find the solution for that whatever mathematical formulation you have done. Interpret the solution in the context of the real world. So it's exactly before formulation, in what language we got it, we found the solution, we tested the solution for various data, and as mathematics person, we agree that the solution is reached. But that's not sufficient for the person who gave us the problem, because he doesn't understand our abstract mathematical language. So it has to be then articulated in or interpreted in the real world context or in their language so that the solution can be reached. And last, it must be validated that the extent of the model is good representation of the actual problem. So that will be done by the user or who has stated the problem, will give us data, we'll check it. Once the mathematically found correct, that whatever expected or whatever observed data is showing mathematically found data and observed data, they two are matching, or we say that the error is less than some epsilon value, then we say that mathematically we have got a viable model and we can go ahead and use it. Now, to use it, what is the stating the problem, identifying relevant factors, mathematical description, whatever I told you is put in a little more words here. Then finding the solution, and this needs a good amount of mathematical knowledge. So this cannot be done by a person who is not aware about mathematics. It must be done very beautifully. But interpretation is somewhere a lot of mathematical people fail to give it properly, because they think always in terms of the way they understand mathematics. So this connect is something which is very, very important, that we are able to convert it back, or the solution should be written in terms of the problem which we got it. So we should connect these two dots. The problem was real life, solution should be real life. And then validating the solution, which is important to confirm that the model is appropriate. So let's take a small example, mathematical modeling example for night time in Norway. Now, in India, we are very lucky that we have around 12 hours of day and 12 hours of night, and little Uttara and Dakshina, and you will have little change in the number of hours. But we have almost equal amount of daytime and equal amount of night time. But not so with the Western world, because those who are very close to the pole, their number of hours keep changing. They have very less daytime sometimes in some months, and very less night time in some months. So how this has to be interpreted mathematically? I'll show you what is done by a mathematics person to interpret why, the reason behind it. So suppose in daytime in Japan is very long, even at 10:40 p.m. it is pitch dark, but at 9:30 it's almost like evening. Now, if we think in India 9:30, we know it's night time. It is not evening. We call it definitely night. But in some areas in the world, 9 o'clock could be an evening where sun is just setting. Now, if we look at it, the concrete model from the real world is like you have the earth and its axis. You have with the parameters on which that particular country lies. Like you take the longitude and latitude of that particular country, and whether it is near the equator, you will have equal amount of day night time. But as you go close to the pole, that will change. So that will be interpreted by the angles at which you are with the actual axis, how much is the turn. So it's called a geometric model if we give only depicting Earth and a particular point at which that particular place for which we are looking, it's daytime. Now, if we make a symbolic model or the mathematical formulation, it's a trigonometric model because it's circular. You know, day and night are always, you will get day after night, night after day. So it's definitely a circular model. So it's a trigonometric equation which comes in. Now, don't ask me the values from where they came. That work has been done by the mathematician by doing lot of data processing, and then finally got that it is 2 by 15 cos inverse of tan 23.4 into tan x, where x is the value of that angle deviation for that particular place. Then the graphic model of the same. So you plot the graph of that particular function and see that it is going round. So now once the graph is plotted where you have the north latitude against the hours of night time. So night time goes on decreasing. If you see the curve is going down. So what it tells is at a particular time, so you can say the number of for particular places on the earth and also on particular months. The mathematical model which we designed this way can interpret that the hours of night time dramatically decrease at a particular point where x is at Norway. But see that it is not so much in the beginning when it is close to the origin, but as it moves to the right, it is decreasing very fast. And this is a way real life problem can be understood. Now, no, we have not solved the problem, but we have interpreted why this happens. Okay, another thing, how do we know whether what is a good mathematical model? Now, I gave you one example, but how do we say a mathematical model is good or not? So the first thing, the model should be simple and understandable. The more complex it is, interpretation of that will be becoming very difficult. And that is why, to make it simple and understandable, we don't make mathematical model for the whole thing, but we divide it into pieces and make the model, and that each of that is understandable. Second is the model should be reasonable. Reasonable in the sense what values we get out of it should not be so like infinity is the answer or never possible is the answer. Then that is not, because it's a real life situation which is happening. So we are not giving a solution to something which is impossibility or non-happening. We are looking for a solution for a happening. So the model should interpret what is looking to be rational or reasonable. Third thing is the model should be easy to maintain and control. Maintain and control means it should not be a dynamic model where every parameter there are some 100 equations. If there are so many conditions, if for this condition, this equation, for this condition, this equation, and then the total control is very difficult because each equation solution process itself is going to be very difficult. You know, some nonlinear equations or nonlinear differential equations become very, very complicated to solve sometimes. So we have to be very careful that it should be easy to maintain, in the sense whenever a data point or when the parametric values are given, we should be able to calculate it within some specified time. And the model should be adaptive. Adaptive in the sense, as I said, if we use the fuzzy logic and get a mathematical model, can convert it into an operational process, then it's called adaptive. So parameters and structures should be such that we can change them into the actual situational or physical parameters which we can see, not simply the abstract parameters of a mathematical equation. But we can see that with the boundary conditions, with the upper lower limits or whatever are the limits within which the parameters should take values, once that is specified, these parameters should become physically possible. Then it model is called adaptive. And last, the model should be complete on important issues. That is, all important variables and factors should be taken into consideration. And this part should be very carefully done when formulation of a mathematical model is done. because while formulating the mathematical definition of the problem, if we have missed out on some important factors, then it will go off. I'll tell you one example. There was Apollo the 13. There was SLV when America wanted to launch a satellite, and Apollo was their satellite launching vehicle. We call it SLV. And they were that satellite to be launched. Everything was set. Everybody said it was all well tested, and everybody was sure, waiting. Countdown started. Everything was checked, and everybody was satisfied with the whole thing. That 10, 9, 8, 7, 3, 2, 1, 0 happened, and the blast was made. The expectation was with the blast, you know how the satellites are launched. So the lower rocket launcher will actually push the rocket into the orbit. By that, what should happen is the lower part comes down and the upper part of the rocket moves into the trajectory. But instead of throwing the satellite into the space, actually everything got blasted at the bottom only. Now, there was a lot of money was wasted, a lot of time was wasted, but they did research and found out what happened. Why did this happen? So some factors were not taken care. Some program which was actually put to process that SLV was not tested, and for some particular data, that whole thing went into an infinite loop. Now, when it went into an infinite loop, instead of when it blasts, they two have to leave. They two have to leave each other. That means there has to be a separation of the variables. But instead of that separation, it went into infinite loop and everything blasted. Then they found out at the model level itself, they had missed out what is the possibility of that division by zero kind of thing happened. And then it went into infinite loop and blasted. So if some important factors or variables are missed out while defining the problem, then what will happen is some important issues will not be taken care. You are seeing nowadays some electric bikes blasting out, or people are now very scared with that. We should not be scared about it, but now they are researching on which parameters have not been taken care. Maybe different temperatures, different weather conditions are giving issues there. Okay. Now, advantages of modeling. Use of model avoids constructing costly plants or warehouses or locations, and it avoids your cost on creation. Model indicates gaps that are not immediately apparent by naked eye or by the observation which is done. Mathematical model will tell those issues. Models have advantages of time, since results can be obtained within relatively short time. Instead of waiting for the whole process to happen, mathematical formulation can complete it without waiting. We can just substitute different values of t instead of waiting for the time cycle to complete. The substitution is sufficient. We don't have to wait. If it is physical, we have to wait for the whole time cycle to complete. The next is because the constant squeeze on profits, cost and time saving on the models allow the decision-making tools greater value to the manager, because it's very important that anybody who why they want to spend on mathematical modeling is it saves their total cost on manufacturing, constructing, designing. Before that, they have done the viability testing with the mathematical model. So the manager, whoever is the project manager, is sure that if at all now we go ahead with actual construction or design, we will not have big loss. So I will give you a few small examples where you will see now mathematics, because till now it was almost like a theoretical lecture, you may assume. But now let's look at some mathematics where an interesting topic for many of us could be how an aircraft is designed, why the aircraft has those shapes, when a car can be rectangular or a box-like, when a scooter can be a sleek engine is in the center and two wheels, and that's sufficient. But you must have seen the aerodynamic process which requires the aeroplane to take off from the land. Now that I'm going to show you how mathematical model has helped in designing the aircraft. So aircraft modeling has variety of designs. So we will look at only one of it, that is the body fixed coordinate system of aircraft. So body fixed coordinate system, if you look at the aeroplane, look at it like a mathematical, you have a picture into a three-dimensional XYZ axis. So look at its body axis. At what point it will remain stable? Because if it is, it has to be stable, we should know in which angle it remains stable and what are its wind axis. When the wind is tailwind, like coming from behind or coming from front. We call tailwind is from the back and front is from the front. So the axis system, the way it is shown here, the XYZ axis, you can look at it. Y is the body axis, Z is the body axis, X is also the body axis. X is the front where you see the nose, Y is towards the perpendicular to X axis, and Z is the vertical, so the third dimension of it. Now, angle of attack. Attack is where the nose is coming in, and we have the angles to be appropriately put in if the airplane has to take off. So the total speed. So if you have observed, if you have traveled in an aeroplane, before it takes off, even while standing, it would take a turn, come on the runway, and it will raise its velocity even while being stationary. Lot of sound you will hear, like grrr, it will do. It will raise its velocity and then start. So it can take that takeoff velocity, as it is called. It reaches to the takeoff velocity within the runway and then takes it off. So if the aeroplane has to go, it has to have the longitudinal mode and lateral mode, because it has to be horizontally stable, it has to be longitudinally stable. So that needs two equations, the longitudinal equation and the lateral equation, and they two must be coupled with each other. These looks to be, the degree of freedom will be there in like 1, 2, 3 and 4, 5, 6 different degrees of freedom are given in. But the velocity is not one directional velocity like you see in your speedometer on your scooter. Will tell you only a linear, like you are going straight, that's the velocity at which you are going. But here we have to know, because there is a wind which is flowing. If you are having same thing to be done for a boat, you have solved problems on boat. Like if you are going against the water or you are going with the wind flow of the water, then you know that you add or subtract the speed of water to the actual steady state velocity. So you know that for water flow, exactly similar thing has to be done for the wind flow. What we did for water flow for a boat, similar thing has to be done, and you have to do decoupling of longitudinal and lateral modes. So if we look at four forces which will act for a aeroplane to be stable on, like person sitting inside the aeroplane should feel stable though the aeroplane is moving. That's the whole beauty of these aerodynamic processes. So what it does is there will be a lift because the aeroplane takes off. There will be a thrust in the front because it has to cut the wind flow and go. But there will be a drag, or if the flow is on the reverse side, and the weight of its own. Like that's why, you know, in an aeroplane, you cannot carry as much weight you want. They will say 15 kgs per person is allowed, because there will be some weight balance will be done, that weight should be, to take off, the weight cannot increase by so much so that the plane doesn't come down. So they will definitely not allow you, if the total weight is exceeding, you cannot carry. They'll just throw if you have extra weight with you. But that equation, see, it looks to be like a vector equation, and you can write that this would be something done mathematically without even the flying of aeroplane. And you find out it's a simple first order system if you look at the dynamics of the aerodynamic process there. It's not so simple in, but now look at it. If the aeroplane is going straight in its line, it's fine. But the aeroplane will not go simple straight. It's not like a straight road on which you are driving a car or your two-wheeler. The road itself is not known in that place, so we have to have the trajectile motion. For that, maneuvering, that is the movement of the aeroplane, has to be very appropriate. You must have seen on 26 January when in Delhi we have those air show of all our military aeroplanes. You see them coming zoop and going upwards. So to take it upwards, there is a big mathematical equation processing which comes like it depends on so many parameters. So straight flight will have the initial values, symmetric flight if it is balanced on both sides. So if you will observe this in an aeroplane, if the number of seats are say 70 and there are only 30 people, then the aerostess will come and say, please don't sit all of you in front or all of you at the back, but she will distribute people to sit in such a way that the weight is balanced on both sides, because that symmetry is very, very important. Otherwise, the aeroplane will have issues. So these small things are mathematically taken care before actually it flies, and now they become instructions for us to go ahead. Now, simple thing which you will understand is a fifth order eigenvalue characteristic equation of the matrix which decides the previous equations. I'm not going into every step in, but it's called the stability matrix. That stability matrix has fifth order because of so many parameters which come in, but its eigenvalues which are found because of the characteristic equation, what it tells is if the eigenvalue is there, then it can spiral, or it will go round, or it will go to the left, or it will go to the right. That 5 different directions it can take. The 0 is the steady state. E and F are two, left and right it can go, but the other two are the ones where it has to be taking the maneuvering to the spiral one. So if it has to go spiral, it has to understand all these things. So before actually making all this gymnastics of aeroplanes, all this will be done on paper, it will be understood and then made. So if we have characteristic equation, what you write the determinant of A minus lambda I, then it will actually move like this. So if this maneuvering has to happen, there has to be some turns. You have seen all this happening in the air show, but how exactly they do it? So there are a lot of parameter adjusting the captain of the aeroplane has to do by changing the lever so that the direction will change, it will spin, it will viral, or it will move in appropriate direction and move it. So at different points which I showed you, A, B, C, there will be the change in the direction by changing that particular eigenvalue there. So now with that example, we understand that problem definition, analysis, modeling, either you go by data processing or go by simulation, then do validation, test your validation into the problem definition and declare that it is working, or the final answer could be it is not working. That is also a rather good thing, that mathematically we told that something is not working, so nobody will go for it. So, okay. So model is only a simplification of a real world problem, and they are not the same thing. You are not having exactly what you saw, but you have now told. So I'll tell you a small thing, like you have, what is the difference between the real life and what is the problem model, mathematical model? So I read it somewhere and I liked it, very nice analogy, that what is the difference between an advertisement about chocolate that gives you the attractive visual experience. If you see a chocolate advertisement on TV or a chocolate ice cream on TV, you will start mouth watering by looking at it, but that is not actually the taste of chocolate. So you eating the chocolate or chocolate ice cream and you watching the ad, how much is the difference? That's exactly the difference between the model and the real world problem. But you can make that experience to convert into reality if mathematically we say it's possible. So let's look at few. Madam, can I go for next 5-10 minutes more? I have few examples.
Yes, ma'am.
Yeah. So math is studied as pure science. Most of the mathematics teachers or students think pure mathematics is the right thing. But all pure mathematics today, all the calculus, algebra, with the invent of machine learning, artificial intelligence, all statistics algebra and your differential equations have been made into, in differential equations were always part of applied mathematics, but the real pure mathematics essence is being used into application by invent of machine learning and artificial intelligence. So I'll give you example of recent COVID-19 impact, where in India a lot of models came out, and that's why you have seen in the COVID app you will see a lot of graphs which will tell you in your 2 kilometers how many people are there, 10 kilometers how many people are there, what is the increase decrease. That app has a lot of mathematical modeling which is done. So basically, there are some susceptible people who can get COVID affection or can get impacted by COVID. They are divided into two, either totally uh, unaware and they go and get exposed, or some people who, without knowledge, they had some kind of immunity and they did not get impacted. So susceptible and who got exposed became infected. So this number goes down, that S to E to I, they come down. But among infected, many recovered and few could not recover. So all these epsilon, delta and gamma were found out by actual data. This was the flow in which the COVID data moved. Susceptible are people who traveled or who had some exposure. They had those contact tracing and all that. Who got exposed where the contact traced, and then who got infected, whose COVID test came positive, and then those who got admitted, who got treated, and who recovered, and who could not be recovered. All this data was available. So how this real world problem was converted to mathematical and then interpreted. So, okay, I think that some graph got missed. I'm sorry, I hope there's a change in the sequence of slides. So suppose you want to know how the brain tissue, blood flow and the spinal canal, all they process. You will have this real life biological problem. I have taken biology very specifically because many people think that biology and mathematics are opposite ends. But today, bioinformatics has made most of mathematics to be studied by doctors and people who do biology. So the boundary value, the flow of blood to brain was studied and a graph was made into. Its graph was plotted with the equation. So the vessel boundary avoidance algorithm. So it should not have, it should not leak out, that kind of process. And then what was defined, these are the parameters which should be defined while we make the definition of the problem, then collect the data, plot the graph and find out what happens to the graph. Convert it, the extreme cases. This is very important in any mathematical model. Large influence of different parameters has to be put in. Small influence we can neglect, as we say, the smaller values can be neglected, but large influence has to be understood, and they are the ones to be studied very carefully, because like we know in blood pressure, if your blood pressure goes above some 180 and below 90, then both are very, very bad conditions. So they are the extreme conditions. Same way, these values of di and dj to be found by mathematically is very important. And then they did a lot of data research, then find out what exactly happens, how those equations behave, find their solution. And then conclusion may, they say that mathematical algorithm provided data which shows the graph in its exponential form, but then it says that up to some point it is okay. After that it goes, and they found out that the actual development algorithm worked 80% accurate with what the results doctor had got. So okay, it has got some movement in the slide. So it has come back to that corona thing: susceptible, exposed, infectious, and recovered. So I come back and say that recovered person is again possible to become a susceptible after some time. So what happens is the raw input data was about many, many people. lot of data was found, and then they fit the data to statistical technique applied and fit it found to be increasing and then decreasing. But then that projection was given into a range that these percent of people had no choice, but once they got exposed, they got impacted. And very little percentage who got exposed did not get. And this information was coming quite regularly for us, and it helped all those who developed the vaccine, because the vaccine testing was also done on the same data. And we should be very thankful to those industries who developed that vaccine for us and saved many of us from getting infected within short time. But there was a lot of contribution by many university mathematics professor and statisticians who allowed and did a lot of work on this data and helped those industries while testing as well as while implementing the COVID app and the models. Okay, so this was an article published in elsewhere, that is influencing public health policy with data informed mathematical models. Why I'm showing you this is, now even the government policymakers accept mathematical modeling process. There are advisors to the government department from the technology and science departments, and they confirm whether these kind of policies for health or education both are required or not, what happens. So mathematical modeling has become into real life, not only in the classrooms, but is much part of the day-to-day processing in industry as well as in lot of government. So this was a thing which you must be aware about. The IIT Kanpur had given a solution for the traffic jams at junctions. So how the model was made, they made a mathematical model, and then now at many places you will find that 4-lane junction where there's like evening hours, or when you say the office hours, there'll be a lot of chaos at junctions. Then they changed that 4-lane road into 2-lane road, and the movement of other crossroads was modeled in a way that the traffic can be slowed down or the jam can be avoided. So how it looked is, so this was a situation in many metros, like if you come to Bangalore, Hyderabad, Mumbai, many roads are, many people will be waiting to reach home. Like office time is 8 hours, traveling time in the evening is 2.5 to 3 hours. Then the one solution given was flyovers, but it's very costly and it cannot be done at every place. It takes a lot of time also to get that flyover, and then have a lot of ways, lot of land has to be, or a lot of time, money, everything to be spent on. So that's also one solution which came up, like you have parallel more dimensions of the traffic travel. This is already happening in many places, but a mathematical modulation by simulation was given this way. Instead of having a 4-junction, this was given by IIT Kanpur, where you find it now applied at many, like Bangalore, I have seen it applied, even Hyderabad, I have seen it. It's made that, like Uppal Junction, I have seen where the college people come from, is that 4-lane junction near the Osmania University, Uppal Junction as it's called, was always a chaotic place. But now what they have done is only 2-way is allowed, and the other traffic has to take a U-turn and join the remaining traffic. So this was given a graph theoretical model with lot of data processing, and it has solved many issues. And this was first given mathematically, and the implementation was very less costly than flyovers. And also it has its own restrictions, because it should have such parallel lanes to move. It cannot be done otherwise. Okay, so to come to the closure, it's a very, Eigen, Manfred Eigen. What he says is a theory has only the alternative of being right or wrong. But a model has a third possibility. It may be right, but may be irrelevant. So don't think that I made a mathematical model means it must be useful. But a model may be totally irrelevant, or maybe giving an answer that it is of no use, or whatever process thought is of no use. But practically, that irrelevant model is also sometimes very useful, because we can avoid such manufacturing designing process and save a lot of money than actually get into problems. So I like this statement very much, that maths is not about becoming a calculator, but become a creative thinker. So mathematicians today should think that they are much beyond basically addition, subtraction, multiplication, division, or solving some equations and substituting and getting values. We can go beyond that by becoming a creative thinker, where we collaborate with real life problems and apply our mathematical creativity, get to solution, and become a better person. So thank you so much from my side. Any questions, I welcome.
Ma'am,
Yes.
you have given a clear and detailed explanation about the mathematical models from alpha to omega, and also this with the suitable real-time application. Thank you so much, ma'am. Now we will go. Naveen sir will take over the question session.
Thank you very much, ma'am. Very good evening, ma'am.
Good evening.
Really, today's session was very helpful for the participants. Right from the beginning onwards, you have given the detailed explanation of mathematical modeling, ma'am. And even you have given the different types of models which we come across while doing this mathematical modeling. And even you have discussed the various steps we need to follow this one. Really, it was very informative, ma'am.
Thank you.
With your permission, shall we go for the questionnaire session?
Yes, please. Yes, please. Anyone
Yes.
has any?
So yeah, if any participants would like to have queries regarding this session, so please you can unmute yourself and you can ask, or you can raise your hands, or you can post your questions in the chat box. Ma'am, actually, I have one doubt, ma'am.
Yes.
So as you said, we have the different models in the mathematical modeling while solving this one. So if any research person wants to do any research in this mathematical modeling, so how you need to select the data, ma'am? That means the data should be, which data should be useful for which model? How you need to justify that, and you need to select the data.
Sir, please clarify, you want to do research on mathematical modeling, or in your research you want to use mathematical model? Because these two are different things.
Yeah, in mathematical modeling, ma'am.
You want to do research in mathematical modeling?
Yes, ma'am. Yes.
Okay, then you will have to take different types of models, and then each model has different type of data. As I told you that if it's a discrete or continuous, so you will have to take examples to say which one is better can never be stated. That's first thing about mathematical modeling. There is nothing like versus. This is better than that is never a story. So if you want to come out with research which will say that this kind of data suits to this kind of model with these kind of parameters, then that you should know all the data which I have given in this. Take real-time examples. Now today fuzzy is something which is very important, because without fuzzy nothing new is coming up. Second is large data, which can be like your Aadhaar number and telephone, or human personal data, how that large data can be handled with algorithmic process, because small data handling today nobody would be interested in. The third is the simulation processing. Simulation majorly is used on, like I gave you example of car driving or flight driving, or anything where there is a danger. Any such data can be first simulated and then put in. So you can do it in three directions, saying that I have this kind of data. Looking at this data, how do one decide which model, which mathematics can be applied? That would be good enough. Otherwise, it has to be like known data to unknown solution, and then the mathematics has to be put in. So that part is very well actually available in a lot of papers. So if you want some references, I can give, because mathematical modeling is into industry in full length today.
Yes, ma'am.
Okay.
Ma'am, one more question, ma'am.
Yeah.
Suppose, as you said, that conclusion part, that validation and the results are very important for this mathematical modeling.
Yes.
So to conclude this results, whatever we have done here, so which will be the more effective one, that software which helps us to get the accurate results of this?
Not necessary, sir. Say, like, for example, if the large data, we have to develop algorithmic or software processing. But if the data is like, for example, if you are like in your own colony, you have a, suppose, simple example I'll give you. There's a large colony with 250 houses, and you have to build a community center, or you have to decide the timings for the gym in the community center. This is to be done mathematically. Now, if this has to be done mathematically, you have to find out how many younger people, what age groups, and what are the parameters which are affected by the gym. Now, if gym is the only thing we want to solve, how much time the gym should be kept open, or how many instruments should be there. These two are generally problems which are solved by many people in simple example. Now, for that, you don't have to go algorithmic or process. You just have a linear or quadratic equation if it fits, or whatever differential equation it fits, because there is rate of change. People come for some time, they spend some time. So there is definitely rate of change of number of people coming there. So in this case, you just need actual data, but it will vary on holidays, vary on vacation days, vary on weekdays. So such different data sets you have to create. So basically you will have to find out different data types which can come in, or different data sets as we call it in algorithm process, and test it for that. That validation is sufficient. But if it is a large data which you can get, like COVID model, then it needs algorithmic process where you have to have large data process. But again, in that also, they did work out. That's why the vaccination started for only for comorbid patients first, and then they went on going by age groups, because what data they gave was the number of people in that age group and who needs first. So these two parameters were put in, and large data was processed, and the conclusion was put in. So sometimes we don't have to do testing on all data. We have to test little data and then extrapolate the results. Both is depends on what the situation is. Okay.
Yeah. Yes, ma'am.
Yeah. Somebody has put in, Sanjeeva has raised hand, and one student had put the
So one participant
black
is,
box and white box. Somebody had asked two examples.
yes,
Okay.
ma'am.
Yeah, so black box model is like I can tell you the washing machine and AC I told you. It is totally unknown things. There were no data available on whether it's possible or not, or unmanned car driving. These are all like, you cannot have a car running without human and then check the data and whether it's valid or not. So that's called a black box model, where you have no way to get the data because you want to do something which is beyond possibility of getting data. So black box models are not very rare, but they need very careful handling because you are going beyond basic possibilities. But white box model is where most of till now done experimental or observation process is white box model. Like your blood sample, like there are O, A, B, C different groups, and which blood group can give blood to other group. So they definitely had some issues in olden days. Then they tested their blood groups and then checked in chemically, they checked which will have chemical formations, and then statistically they checked because they had data, and then there was a model and then made it. So white box models are many. Black box models are very carefully to be handled because nobody is aware about what could be the data and what could be the results, and that's why the testing is done very carefully. Especially like you have the metro, bullet train without human driver, it is the machine made, but all that is done under simulation and then tested. So I hope I gave you the understanding of black box model and white box model.
Yeah. Any questions?
Somebody,
any-
Sanjeeva, has raised his hand. Can ask the question.
Yeah. Anyone, if you want to ask any queries, please you can raise or you can just put in the chat box. I think.
Yeah.
Yeah, I think no one, ma'am. So
Okay.
thank you very much, ma'am,
Thanks.
for answering the questions with a lot of patience, and you have given a lot of informative information. Thanks a lot.
Thank
Over
you.
to Sujata, ma'am.
So now Ms. Nandini, student of second MSc Mathematics, will propose the vote of thanks.
A warm and graceful evening to our most valued Honorable Chief Guest, Dr. Indrani Pramod Kalkar, faculty members, and research scholars. It's my honor to propose the vote of thanks on third day of 5-day national level online PDP on writing research articles in mathematics and statistics. Henry Ward Beecher calls gratitude as the fairest blossom which springs from the souls. On behalf of Little Flowers Degree College and Auxilium College, our special thanks to the resource person, Dr. Indrani Pramod Kalkar, for sparing her valuable time in spite of her busiest schedule to grace this program. Ma'am has given deep insights of mathematical modeling with lot of real world examples, which is followed by types of models, which is very essential in understanding mathematical modeling problems. Some of them include static or dynamic model, discrete or continuous model, linear or nonlinear model, deterministic or probabilistic model, explicit or implicit model, quantitative or qualitative model. Ma'am have given clear explanations on how real world problems are classified into black box model and white box model with numerous day-to-day life happenings as examples. Ma'am has also discussed other types of models including linear model, exponential model, quadratic model, trigonometric model, cubic model, reciprocal model, logarithmic, and logistic model. Depending on the type of models, we can predict what kind of mathematical parameters have been used in it. Mathematical modeling provides a framework in which we can formalize our assumptions about the processes we are trying to capture, build them into a simplified representation of reality, and simulate forward in time to suggest what might happen in the future under different policy options. We have learned classification of models on different categories, which include models based on object of study, models based on model operator, models based on modeling goals, models based on implementation methods, which is followed by the steps involved in mathematical modeling, including formulations, finding the solution, interpretation of the solution, checking the good representation of the problem with real world examples. We have also learned characteristics of good mathematical modeling through real world situations. Ma'am has given deep insights of advantages of mathematical modeling, which is followed by the concluding part of the session, that is designing aircrafts using mathematical modeling. And we have learned how real world problems are converted into mathematical models and interpreting them. Your talk has enlightened Your talk has enlightened our mind and have shown a new path in the field of mathematical modeling for researchers. The participants would have received many informations which will help them to find a new direction in that area of research. Last but not the least, I thank all the participants. Thank you, one and all.
Thank you, Ms. Nandini. Ma'am, thank you so much, ma'am.
Nice. Thank you, Sujata madam.
So
It's
it was
great honor
mesmerizing. We don't know what to say about your speech. From the starting till end, we were without any distraction.
No, the
Student,
way
even our students
Nandini,
were
no, I'm
listening to
really
your
amazed. Madam, I'm amazed. Nandini has put every point in my PPT, which I wouldn't also remember if it had to be put in 2 minutes. So I'm really happy that she has heard everything what I said, and 66 people are still there is something good. So congratulations to all of you for conducting such things where professional development will happen and should happen, and all the best to all the participants and you both colleges to do something great in this one. Thank you so much.
Thank you, ma'am. Thank you so much.
Thank you, ma'am.
Participants, kindly switch on your camera for the photo session.
Yeah. So please switch on your camera so that we can take a screenshot with our resource person. Thank you very much, participants, for just enabling your cameras and being with us for such a long time. Thank you.
Thank you. Thank
Thank
you,
you
ma'am,
very
once again.
Thank you, madam.
Feedback link is posted in the chat box.
Yes.
Participants, kindly fill the feedback.
I can log out, right?
Yes, sir.
Yeah.
Yes,
Thank
ma'am.
you.
Thank you.
Thank you.
Yeah, please fill the feedback form which is posted in the chat box.
Participants, kindly don't share the feedback link in the WhatsApp group. And once the session is over, the feedback link will be closed.
Hello. Sir, could you please send the feedback form, sir? Yesterday also there was a problem. Yesterday also we faced the same problem, sir. Please send the feedback.
Yeah, I request all the participants to please fill the feedback form, and you people can leave after completing your feedback form. Session is going to close. Please fill your feedback forms. After completing the feedback forms, you can leave the session. Performance.